Okay, 5.5. The fundamental theorem of calculus. Could it sound any more important? There's fundamental theorems for arithmetic to do with prime factorizations, for algebra to do with finding roots, and apparently there's one for poker. We talk about calculus. Okay, we're going to talk about differentiating an area function, and we're going to talk about essentially the secret to how to calculate these things. Okay. So how to use antiderivatives to find areas. Okay, so that's from the end of our very first class, and I said the area of the area problem and the tangent problem are solved in similar-ish ways. Okay, you build approximations, you refine the approximations, and you see what the refinements do in the limit. So they're solved in similar-ish ways, and that's how we build the two great tools of calculus: the derivative and the integral. Prepare to be annoyed, because this is the picture I put up at the beginning. There's another intimate connection between these two things, and that's what we're going to talk about today. Okay, and that should come as a surprise, okay, because the area problem and the tangent problem seem different, okay, the derivative and the integral seem different, and yet there's a really, really close bond between them, and that's today's subject. Okay, so if you're annoyed by the cuteness, this should make up for it. These are the guys responsible for what we're going to talk about today. What do we got? James Gregory, Isaac Barrow, Isaac Newton, Gottfried Leibniz, who appears to have several animals on his head. So they came up with this and developed it. Gregory did it geometrically, Barrow came up with more, and the other guys developed it, and you've heard their names before. Okay, so let's talk about part one of this thing. Okay, so we're going to suppose we have a function f that's continuous on a closed interval from a to b. Incidentally, whenever I say area today, I'm going to mean signed area, okay? So fill that in your head. So I might slip up and not say signed sometimes. Every time I say area today, I mean signed area, so net area. Okay, let's draw this guy. A to B. Okay, it doesn't have to look like that. Okay, it's your graph of F. And we want to look at the signed area under this thing, between this thing and the axis, up to a point x. Maybe I'll move my B along. Okay. All right. Positive contribution, negative contribution. Positive contribution. Okay, so we have a continuous function on an interval, and what we're trying to on a closed interval, and what we're trying to do is we're trying to find the signed area up to x. Okay? And x can be anywhere between a and b. So let's define. I might do this on the next board. Okay, so let's define a function, big A sub little a, given by this definite integral. Okay, what does this tell you? This tells you the signed area from A to X, between that function and the axis, okay? And the horizontal axis. Okay, so this is the signed area so far function. Or net area so far. Okay, up to X. Okay. And as I said before, X can be anywhere between A and B. All right, for any particular value of X, okay, we're going from a number to a number, okay, so this thing is going to be a number, okay? So for any value of X, this thing's a number. And again, definitely not a function of t, because t is that dummy variable, it goes away. When we make X a variable, this thing becomes a function of X, okay? All right, so this is the function of X that tells us how much area we've got, signed area from A until X. It's a function of X, definitely not a function of t, because t is a dummy variable, and it goes away once we take care of the integral. Any questions about that? Okay. Okay, what happens if we colored okay. All right, so what happens if we step forward a bit? Okay, so we step forward a tiny bit h. Let's see what happens. Okay, so that's x plus h. Okay. Oh boy. Okay, so that amount that we've stepped forward is h. Okay, we want to see what happens to the signed area as we take a step forward. A small, small step forward of size h. Okay, this distance, okay, is the value of the function at x. Okay, so this is just f at x. Is that all good? Okay, that's f at x, that's h, and we want to see what happens to the signed area as we take a small step. Okay, so the new area, so the area up to x plus h, is approximately the old area up to x. Okay, so white stuff plus h times f at x. If that's invisible from the back, tell me. Is it invisible? That's nice, isn't it? What's funny is when I use other colors, they look like white. So it's either invisible or they look like white. Here you go. Okay. Good. Excellent. So, basically, okay, so we're going the signed area up to here is the signed area up to here plus this bit. Okay, and we're saying if h is small, then that is pretty much a rectangle. Okay, and the area of that would be h times f at x. Okay, so that's how much we add on in that step. Okay. And signed area works too, right? If f at x was negative, we would take off that much area. So this all works out. Okay, we can rearrange this thing to look suspiciously familiar. If I bring this guy to this side and divide everything by h, what do I get? For the record, most people don't put this subscript a. I think it makes things clear. If you want to skip the subscript, you're welcome to do that. Hey, that looks familiar. It's a difference quotient. Okay, that's an approximation for a small step h. Okay, what if I take the limit as h goes to 0? Then that approximation becomes exact. That looks more and more like a rectangle. The rectangle more and more approximates the area of that strip. Okay, so let's take the limit, and this thing becomes exact. Incidentally, this is a somewhat sketchy proof of this. If you want a real proof, look in a textbook or ask me. It's pretty much all stuff you've seen before. Things like extreme value theorem, squeeze theorem, that sort of stuff. Okay? But this is a decent intuitive-ish proof. Okay. All good? What's that thing? Derivative, yeah? Okay, difference quotient, derivative. That's it. Okay, you don't have to write all that. We've talked about it. That's to make it look official. If you want to write it, you're welcome to. Okay, so what are we saying here? We're saying that the derivative, okay, of the area function, of the area so far function, is equal to f of x. For all x between a and b exclusive, and remember, f had better be continuous. There you go, that's it. That's part one of the fundamental theorem. This is this fantastically important thing. That's all there is to part one. That result. Okay? So what are we saying? We have a definite integral, roughly speaking. The derivative with respect to the upper limit is just a function evaluated at the upper limit. What is this? This is the rate at which we accumulate area. Okay, and we're saying that the rate at which we accumulate area is given by the value of the function at the frontier. Okay? The rate at which we accumulate area is just the value of the function at the frontier. Call it f. That makes perfect sense, okay? Again, the rate at which we add area is just the value of f here, okay, at the frontier. Okay? So for example, if f was huge, okay, we'd be adding area quickly. If f was negative, the signed area would be falling, okay? That should be reasonably intuitive. That's all this said, okay? Okay. There's an interesting fact here. Roughly speaking, we had a function, we took its integral, and then we took the derivative of that. The derivative undid the integral and gave us our function back. The derivative undid the integral. They're inverse processes. So that's essentially, integration and differentiation are inverse processes. One undid the other. They're inverse operations. Okay? What else does this tell us? Any continuous function has an antiderivative, okay? Because look, if we take the derivative of this thing, whatever it is, we get this, okay? So any continuous function has an antiderivative, okay? Namely, the area so far function or any of its shifted friends, okay? That doesn't mean you can write the antiderivative in a particularly nice, friendly way, but it has an antiderivative. Every continuous function has an antiderivative. And we're about to play with antiderivatives now. Questions about this stuff? Okay, raise hands nice and high in case I can't see. Okay. Hopefully I don't need you anymore. Part 2. Okay. Suppose we know some particular antiderivative of f. Let's call it big F. Some particular antiderivative big F of f. Okay, we have some experience in finding antiderivatives. We'll get more next class. Okay? So suppose we know some antiderivative of f. But what did we say here? The derivative of the area so far function is f. So the area so far function is one of the antiderivatives of f. So the area so far function is also an antiderivative of f. By that. Okay, by part 1. Okay, given certain conditions, we know that if we have two antiderivatives, no question. Given certain conditions, we know that if we have two antiderivatives, they must differ by a constant. Okay? So, the two differ by a constant. For all x in the unknown. This is a constant, the kind we've seen before. Okay, again, these guys are both antiderivatives. One of them you just happen to know, okay? One of them is that mystical area so far function, okay? Because they're both antiderivatives of this thing, they must differ by a constant. Okay? Now check this out. What happens if I subtract the values of the antiderivative at b and a? Just plug into that, okay? At b, at a. All right, people. When I expand this out, you're going to get c minus c. The c's are going to cancel. What's the area from A to A? 0. Thank you. Okay, the area from A to A is 0, or you could write that integral going from A to A of f at t dt and see that that's 0. Okay, hey, look at that. What are we left with? And you go, holy crap. You subtracted those three things, and what did you get? You got the area from A to B. And that's the big important result. The area from A to B okay, is equal to the difference in the values of the antiderivative at the endpoints. Again, for little f continuous from A to B. That's the same thing, except in print, so it looks official. Exactly the same thing. Okay, if you got f continuous on the closed interval from A to B, you get this result. The area from A to B, or the signed area from A to B, is given by the difference of the values the antiderivative takes at those endpoints. And that's what that says. Okay, doesn't matter if you call it t or x, it's a dummy variable, call it whatever you want. Okay? That's the big important result. That's the result of part 2. That's the one you're going to be using a lot. You're going to be using this a lot. Okay? All right. We said big F was an antiderivative of this thing. So this thing is the derivative of big F. So what does this tell us? This tells us that if we differentiate big F, okay, again, sort of, roughly, sort of, if we differentiate big F and then take the integral, we sort of get big F back. Okay, so again, differentiation, integration, inverse process. Okay, part 2 is also called the integral evaluation theorem, because if you want to evaluate this integral, you use this. Okay? Okay. Now again, this is an incredible fact, okay? If you want to calculate this definite integral, okay, so of a continuous function from A to B, so perhaps you want the signed area from A to B associated with that function. All you need to do is spot an antiderivative of the function, evaluate at the endpoints, subtract, and that's it. Okay? Life's easy. So all that Riemann sum, taking limits, all the how do we figure out these areas, all the do we have to know these geometric shapes, all of that goes out the window if you can find that antiderivative. If you find that, evaluate the endpoints, subtract, and life's good. That's all you need to do. No more sums, no more half an hour spent developing these things. You can do it in about 4 seconds. Okay? So this makes life livable. Example. Here's something we've seen before. The integral from 0 to 1 of x squared with respect to x. Okay? Okay, so we're trying to integrate this guy from 0 to 1. First, what did I say? F has to be continuous on the interval. So, is F continuous on the closed interval from 0 to 1? Yes? Yes, good. Okay, it's a very nice polynomial. It's going to be continuous everywhere. It's certainly continuous there. Life's good. We can use this thing. Okay? Okay, so there we go. So we want to calculate this thing. So we need to find antiderivative. What's an antiderivative of x squared, people? Good. That's good, too. Thank you. Good. Excellent. Okay, so an antiderivative would be x cubed over 3. That's an antiderivative. Anyone will do. Okay, that's it. Evaluated the endpoints and subtract. Okay, the endpoints are 1 and 0. Evaluate that guy there. 1 cubed over 3 minus 0 cubed over 3. That's just 1 over 3. How much easier was that than what we used to do? Okay. Spot the thing you're integrating, check it's continuous, find an antiderivative of it, evaluate at the endpoints, subtract, you got your answer, you're finished. Okay, I'm going to forget this if I don't say this now. For the previous lecture, we didn't do too much with the properties, okay? So I put up a PDF involving 2 of the integrals we already evaluated. So given those 2 integrals we already evaluated, move stuff around, flip things around, glue things together, and find some other integrals. All right, so look under my name on Learn. There's a PDF, another extra exercise. That's there now, and I'll put the solutions up tonight, okay? If you got any questions, let me know. Okay, so it's just playing with the properties of the definite integral. Okay. There you go, that was easy. Okay, also try, this is on your own, also try to show, by essentially the same method, from 1 to 5, x squared over 4 dx is 31 over 3. One more minute, people. If you need to shuffle quiet. Okay, that's a result from tutorial. You can find that out this way, and it's a lot more painless than it was in tutorial. Okay, shorthand for this sort of thing. Okay, you can write it like this. Or you could write it like this. Or you could write it like this. Okay, very, very common shorthands for this. You don't actually have to say the letter F explicitly. Life becomes nicer looking if you do that. Okay, so for example, instead of this, you could have just written x cubed, x cubed over 3, 1, 0. My final thing that I'm going to say today. Any antiderivative works. Any antiderivative underlined, okay? We didn't say which antiderivative was. Any one will work. So any antiderivative, you could, again, you could have used x cubed over 3 plus 642. That's also an antiderivative. That would also work. Okay? That's a stupid thing to do because it would just cancel out in the subtraction. Okay? So any antiderivative works. You can pick the simplest one. That will work. Okay? That's time, everybody. I will finish this on Monday. If you have any questions, let me know. Have a beautiful weekend. Thank you. All right, happy Monday, everybody. We're on, no questions? We're on lecture 5.5, Fundamental Theorem of Calculus. We started by constructing an area so far function. We took its derivative and found that it was interesting. And that was part 1 of the fundamental theorem. This is part 2. And we will, what else did we do? We computed a definite integral using this. We discussed it. We said how easy this makes our lives. And now we're going to talk about it a bit more, and that'll be that. Okay. I'm going to try to big up this thing a few more times. Again, you saw this last time. This is part 2 of the fundamental theorem. Again, this should be interesting, right? If you've got a function that's continuous on a closed interval and you want to integrate over that, all you have to do is evaluate an antiderivative of that function at the endpoint, subtract, and that's it. Now this again, I'm going to keep saying this, this should be weird, okay? The definite integral has to do with what f is doing over that whole interval. And yet we can evaluate this thing by just evaluating the antiderivative of the endpoints, okay? So you want to know something about what a function is doing everywhere in an interval, and yet all you need is 2 values associated with the endpoints. That's weird. The reason that sorcery works is because, as we saw last time, antiderivatives are essentially a constant away from being an area so far function. Okay? So that's what we saw last time, and that's what causes that to happen. So that's what makes this miracle possible. Okay, you may remember I mentioned displacement and velocity a few times, and I said that you'll see it again, and I said you'll see it in this class, and this is why. You can call this an example, whatever you want to call this. Suppose it's a position function. The position at time 2 minus the position at time 1. Okay, what is that? That's the net displacement. The change in position is the net displacement from time 1 to time 2. And I said that we found that that was given by the area under a velocity time curve. The signed area under velocity time curve. So from t1 to t2, you integrate the velocity. Again, position, velocity. Okay, well this looks suspiciously like that, doesn't it? So we have what? We have velocity, and we have position, an antiderivative of velocity. Okay, or in other words, we have position and velocity, the derivative of position. That looks a lot like that. Okay? So in effect, we've seen this thing before in the context of position and velocity. Okay? Again, that's net displacement, and that's the signed area under a velocity time curve. Okay. One more example. Example. We evaluated a definite integral last time. I gave you one to do on your own, which I think was a verification of something. And now let's do one more. Suppose we want the definite integral from 0 to pi over 2 of sine x, nice and simple, sine x dx. Okay, what are we talking about? Sine looks sort of like that. 0 to pi over 2. We're after that area. Okay, or signed area, but it's the same as the area because we're upstairs. Okay. Usual check, is this continuous on the interval? Yeah. Trig functions are nice. What's an antiderivative of sine, people? Almost cos? Good, cool. Minus cos. Okay, if you're wondering why, if I take the derivative of cos, I get minus sine. So the derivative of minus cos is sine. Okay, minus cos. We're using that. And I'm going to use this notation. Zero pi over 2. This is all stuff from last time. Applied. Again, what was I doing? This was our function, or our integrand, and I checked that it was continuous on the interval, 0 pi over 2. And this guy was an antiderivative of that. And all we have to do is evaluate that at the endpoint, subtract, and you've got your answer. Let's go here. So, minus cos pi over 2, minus, so this minus this, minus cos 0. Okay, cos at pi over 2 is 0. So you go minus 0, minus minus, or plus. Cos at 0 is 1. Would you look at that? 1. That should be weird, okay? That area is 1 should be weird, okay? But it is. Okay, questions about this? Okay, again, if you're worried about the variable names, that's a dummy. You could have called that whatever you wanted, unless the problem gave you something. Probably keep whatever the problem gave you. And over here, this is really just a variable sort of placeholder to define or describe this antiderivative. You could have sort of called this whatever you want to. Typically, use the same variable as you had over here. Okay, questions? Okay, and again, that area is 1. On your own. On your own doesn't mean it's hard at all. Try verifying something that we showed the previous lecture using symmetries. If you integrate from 0 to 2 pi cos of x with respect to x, you get 0. Okay, we showed that last time using pictures and symmetries. You can do it this way too, and you'll get that answer. Questions? Okay. Okay, at the risk of repeating myself a million times, you can't overstate the importance of this thing, okay? This lets you solve a lot of integral problems really easily, okay? We used to have to use Riemann sums and limits. We don't anymore in appropriate situations. You don't need ingenuity to calculate things like this, okay? Even a schmuck like me can do it, okay? You just do that. Life's good, okay? This is a good thing. That said, there's still an important place for numerical integration. Some of you did that project where you saw numerical differentiation using finite difference quotients. So when you have data and you want to approximate a derivative, or you want to get the closest thing to a derivative, you might use something like a finite difference quotient. Similarly here, if you've got data points, okay, so measurements, and you want an integral, you don't really have a function, you can't really do this kind of thing. So one thing you could do is you could fit a function to it and then calculate the integral, or you use some sort of numerical thing, you put rectangles under or trapezoids under, and you calculate the area that way. Now, more interestingly, sometimes there isn't a nice expression, you don't need to write this down. Sometimes there isn't a nice elementary expression for the antiderivative, okay? So you can't really do this kind of thing in any sort of usable way. So here's an example. This is the probability density function, or a probability density function of the standard normal random variable. Again, you don't need to know this. Okay, so this is incredibly important in probability. It shows up a lot, partly because probability has its own sort of fundamental theorem called the central limit theorem, which is unbelievable. If you scale and shift this thing appropriately, you can model all sorts of things with this. Okay, so suppose, scaled and shifted appropriately, this was a model of, let's say, the distribution of heights in a population. And notice this is a bell curve. Suppose you wanted to know the probability that the height of a randomly chosen person is between here and here. Okay, or you want to know the proportion of the population whose heights are between here and here. What you wind up having to do is integrating here. Okay, you wind up wanting this area under the curve. Okay, so it'd be really, really nice to be able to find an antiderivative of this, evaluate at the endpoints, and subtract. Unfortunately, there's no way to do that nicely. This thing, you can't write a simple, nice, elementary antiderivative for it. It's just plain impossible. Okay? So in a case like that, where we really, really want to for something as important as that, we can't. Okay? So this thing doesn't always work. So that's why you resort to tables and computers, numerical things, to compute things like that. Okay. Incidentally, normal is also called Gaussian, after Gauss, and you notice that E and pi are friends again in that equation. Okay, that's it for that one. Any questions? Again, you obviously don't need to know that that's a probability. Just know that these things have limitations.